Okay, let's get the show on the road here this afternoon. Clearly I'm not Dr. Copeland, but he may be back for class on Thursday, maybe not. If he's not back on Thursday, Dr. Chaffetz will take over for that class meeting. And Dr. Copeland informs me that what he wanted me to do in his absence is to talk about sedimentary rocks, particularly carbonate rocks. I understand you've been wasting your time looking at those nasty igneous and metamorphic rocks that don't hold a torch to these guys. These are by far more interesting things to work with. So, as we see, as we go through today, there are different kinds of sedimentary rocks. The previous slide was shots of the White Cliffs of Dover with chalk, dominantly a carbonate rock, which is the bulk of what I'll be talking about today. And the other group of rocks that we deal with in the sedimentary realm are the original rocks. So here an example of some embedded sandstones and conglomerates with the particle size denoting or giving you information about energy conditions associated with the deposition of those rocks. So before we move into sedimentary rocks in detail, anybody here want to give me the definition of a rock? Any old rock, even those igneous metamorphic things?
Rock. A rock is basically an earth material made up of stuff, doesn't it? It can be organic.
Made up of stuff. Okay. What kind of stuff might a rock be made up of? Okay, so in just giving you a general definition of a rock, it would be made up of minerals. In that case, what other aspect about the definition is important?
It has no set composition.
No, that's true. It doesn't have a set composition, but there's another aspect of what a rock is other than a group of minerals. Well, that's the definition of a mineral that's naturally occurring. If I go down to the beach of Galveston and I pick up a handful of minerals, is that a rock? No, that's sediment. Okay? So the definition of a rock is an aggregate of minerals that are bound together. And the ways in which they're bound together will obviously be predicated on, to a certain extent at least, the way in which they form. So igneous rocks, the minerals in an igneous rock are bound together by virtue of the fact that in the crystallization process coming out of the melt, they interlock to give you the solid end product. So a rock is an aggregate of minerals that are bound together. Okay? That's fine, but we want to talk about sedimentary rocks. Anybody want to venture a definition of a sedimentary rock? Jacob's going to try his stuff on me again.
A sedimentary rock is a rock that's basically compacted of sediment. The sediment can be large particles such as those on the earth, can be small particles such as sand, silt, clay particles. And basically being compacted to the point where they now form the large substance and not fall apart in the end.
Okay, so he gets into the second part of the definition that we talked about with a general rock, is that whatever makes up a sedimentary rock, those individual parts of that rock have to be bound together. But what are those things? Yeah. Well, I mean, what are the things that are bound together in a sedimentary rock? Are they minerals? Well, okay, so they could be minerals, but what else could they be? Other rocks, fragments of pre-existing rock. So typically, when you look at the definition of a sedimentary rock, you'll find that it's an accumulation of particles of pre-existing rock that are bound together. Okay? And that's correct. Many rocks and sedimentary rocks fall into that definition quite nicely, but not all sedimentary rocks fall into that definition. So what else is missing from the definition? Okay, that's the other category that we have to mess with sedimentary rocks, that the rock itself might be formed from some form of precipitation, biochemically induced or simply chemically induced. Okay? So the definition of a sedimentary rock is somewhat messier than the definition of any old rock, because there are some components that we have to address with sedimentary rocks that make the definition a little messier. There's one other aspect or one other component in the definition of what a sedimentary rock is that we've not addressed at all. Now, when I ask you to consider what that component might be, think about all those other rocks you've been looking at, igneous rocks and metamorphic rocks this semester. How do sedimentary rocks differ from igneous and metamorphic rocks in the most general sense? Pardon? Now, we'll get to the organic matter in a little bit, yeah. No? Has to be the conditions under which they form, which are low temperature and pressure or surface temperatures and pressures. So sedimentary rocks form at surface temperatures and pressures. Igneous and metamorphic rocks, of course, form at higher temperatures and pressures, and that forms an important component of what makes up an igneous or a metamorphic rock. So sedimentary rocks, and if I get my slide right, okay, so here's kind of the general story. It's an aggregate of minerals or fragments of pre-existing rocks that are bound together, or an aggregate of minerals precipitated from solution. Okay? And then the last part, which we were just talking about, obviously, is that these rocks form at surface temperatures and pressures. That's not strictly true, because what happens is, after the sediment accumulates and gets buried, as it gets buried, it comes under elevated pressures and temperatures because of just the geothermal gradient that you're dealing with when you bury things to depth. But in general terms, we are talking at temperatures that are lower, temperatures and pressures that are lower than would, for instance, cause metamorphism to occur. So low temperatures and pressures, or surface temperatures and pressures, is a good kind of component to the definition. So then the next question becomes, well, okay, where do we get this stuff from? Right? Where do we get the fragments of pre-existing rock? Where do we get the materials that precipitate out of solution? And the aspect of sedimentary rocks that's of importance, of course, is that they are derived from pre-existing rocks by definition. And the pre-existing rocks, of course, can be igneous, metamorphic, or sedimentary. Doesn't matter. And we derive those materials through a variety of processes. The two listed here, weathering and erosion. Okay, weathering and erosion are the processes that generate the particulate material, the fragments of pre-existing rock, and the materials that go into solution to produce the chemically or biochemically induced precipitates that are legitimately defined as sedimentary rocks. Interestingly enough, of course, is the material in solution can precipitate out of solution to give rise to a rock in its own right, but a fairly common aspect of sedimentary rocks is the material that precipitates out of solution around the fragments of the existing rock that ultimately sticks the particles together, which is an important component of the definition, of course, because otherwise it would be sediment. When you stick the sediment together, it becomes a sedimentary rock. So those sedimentary rocks that are made up predominantly of fragments of pre-existing rock are cemented together by materials that precipitate out of solution. So they form part of the generation and definition of what a sedimentary rock is. So the solid products that we've been talking about, the fragments of pre-existing rock, are generally the products of the weathering process, either mechanical and to a lesser extent chemical weathering. So these fragments, these solid fragments that are generated by the breakdown of pre-existing rock, those fragments are eroded, transported and deposited before they turn or are turned into sedimentary rocks by the process of diagenesis. An important component of diagenesis is the process known as lithification. The term lithification then is used to describe those processes that result in the fragments of pre-existing rock getting stuck together. And those processes include compaction, cementation, and recrystallization. Those are typically the three component parts of the process known as lithification. Now, obviously, in the case of those sedimentary rocks that form by precipitation out of solution, they, by virtue of that process, they're stuck together from the get-go, as it were. They don't have to be as concerned with this process as the compaction, cementation, and recrystallization. Compaction, when you think about it, is a logical process. You've got sediment accumulating in the Mississippi Delta, for example. At the time of deposition, you might have porosities on the order, particularly in finer grained sediment like silts and clays, you may have porosities on the order of 50, 60, 70%. Well, what happens is, as you add more sediment on top of that pile, you generate what's known as a sediment load, and obviously it squeezes that on which it's sitting, and when it squeezes it, it compacts the solid particles and it expels water and reduces the pore space that was originally developed at the time of deposition. So there's your compaction. The cementation obviously relates to the interstitial fluids that exist between the individual particles. If those fluids become saturated with respect to, say, calcium carbonate, the calcium carbonate can precipitate out of solution, and when it does so, it precipitates onto the surface of the grains or particles and then binds them together, the cementation process. Recrystallization is a somewhat more complex component of lithification and tends to occur after the sediment has been buried to some significant depth and the pressures involved in the contacts, grain-to-grain contacts, get to be high enough that you can get actual kind of welding together of the grains by recrystallization. And in the process of lithification, there's no necessarily initially defined sequence. In other words, you don't have to have compaction to make a sedimentary rock. If you cement them up early enough, in other words, close to the sediment-water interface, which happens quite commonly with carbonate rocks, for example, they don't undergo necessarily a great deal of compaction because they have a tendency to cement up pretty early in their history. So the three components of lithification can kick in a variety of orders and in a variety of time frames. So the products of mechanical weathering tend to generate the particles, the solid materials that get transported and deposited and ultimately get turned into a sedimentary rock. The products of chemical weathering involve obviously putting materials into solution, and those materials are equally then transported by groundwater, streams or rivers or what have you to different locations, until such time as the concentration of those materials in those solutions reaches a concentration under the right sets of pressure temperature conditions that will result in precipitation, either as cement to bind together the fragments of pre-existing rock, or as minerals that form sedimentary rocks in their own right of the precipitation variety, as it were. So if we look at sedimentary rocks, we can think of them in terms of their origin, in terms of a cycle, or again part of the rock cycle. We start out with weathering, and this is the process by which Mother Nature attacks existing rocks and breaks them down into either solid or dissolved components. Erosion then is the process by which the particles, talking here about the particulate solid material, are entrained or picked up by some mechanism, current. The current could be a wind current or a water current in a stream or river. So the weathering process generates these particles, which are broken down by a variety of means. Erosion is the process by which they are picked up or entrained, and then they go into transportation mode, and those particles are transported, if we use a stream or a river as our example here, they are transported either in suspension or in what's known as bed load, where they roll or bounce along the bottom of the stream. And then ultimately, these sediments will accumulate at some endpoint, presumably in a basin of deposition. So think of in a simple-minded picture of the Mississippi River and the Gulf of Mexico. The Gulf of Mexico is the hole in the ground where the sediment accumulates. The river is the means by which that material is brought to the hole in the ground. And it's important to think of the sedimentary process in a very simplistic fashion, where you have high points and low points. The high points tend to be the source of the sedimentary material that will ultimately give rise to sedimentary rock. The low point, what we would refer to as a sedimentary basin, is where the sediment accumulates through the process of deposition. And then finally, you have diagenesis, the last kind of component. And this refers to all of those things that happen to sediment after it's accumulated in the sedimentary basin. And the things, as it were, that affect the sediments in the basin can be mechanical, bioturbation, for example, organisms that eat their way and chew their way through the sediment, that is affecting the sediment after burial. Lithification that we talked about, where things get stuck together, and after they become lithified into the form of rocks, any passage of groundwater fluids through those rocks can alter the package as it sits there by either dissolving and or precipitating materials out. Do you have a question? Under what? A marine environment. Okay. Well, the transportation, if we use the Mississippi River as an example, as a means of transportation, it dumps the sediment in a marine environment. Okay? And that's an interesting point. Sediments can accumulate and be deposited in freshwater environments, in lakes and in rivers. They can be deposited in continental environments. Sand dunes in deserts would be an example. Or, of course, they can be deposited in marine basins, the Mississippi Delta building out into the marine Gulf of Mexico, obviously. So the environments of deposition in which the sediment can accumulate is highly variable. Okay? So if we look at sedimentary rock types, there are fundamentally two. I mean, when you read textbooks and in the literature, you might see three listed because sometimes people will break out chemical and biochemical rocks into separate categories. But basically what we've been talking about so far this afternoon is about ferruginous and chemical/biogenic or biochemical sedimentary rocks. And the point about ferruginous sedimentary rocks is that they exhibit a particular kind of texture referred to as a clastic texture. Clastic comes etymologically from the Greek klastos, meaning fragment. And if you think about the definition of a ferruginous sedimentary rock, an aggregate of fragments of pre-existing rock, that describes the textural aspects of ferruginous rocks. You can see individual fragments that have been transported independently, brought together, and through the process of liquefaction, stuck together to form a rock. Yes.
So ferruginous sedimentary rock is
sandstone, conglomerate, what have you. Yeah. Whereas this group of rocks, the chemical, biochemical, biogenic sedimentary rocks, can exhibit a plastic or a non-plastic texture. Now, the non-plastic texture that you can form in the chemical, biochemical sedimentary rocks, of course, is the texture is crystalline. And it's a crystalline texture because the process is not unlike the crystallization of minerals from an igneous melt, except obviously precipitation and sedimentary rocks is occurring at essentially surface temperatures and pressures in which the minerals grow together in a crystalline form, and that would be a non-plastic texture. But there are sedimentary rocks in this category that will exhibit a plastic texture where you can see individual fragments. And we'll see examples of that as we go through the talk today. I put this thing at the bottom because you like to think of things as being all very nice and well organized in life, everything fitting in its own little pigeonhole and so on and so forth. But there are examples of what we call sedimentary rocks that don't fit into either one of these categories. And organic sedimentary rocks fit into that category. The most obvious example being coal. Okay, coal is not made up of minerals that are inorganic. It's made up of organic material, and is commonly formed and associated with what we would generally recognize as being sedimentary rocks. And so coal is often talked about in the context of being a sedimentary rock. Although if you look at the strict definitions and so on and so forth, it doesn't necessarily fall into that category. So you should always be aware of the kinds of outliers that exist in nature. Okay, so ferruginous sedimentary rocks, they comprise particles of pre-existing rocks that have been cemented together. And the point of importance here is these particles, during the life history of their development, behaved independently of each other during the process of erosion, transportation, and deposition. So you can imagine, if you will, the individual sand grain being bounced around and as it's being transported and ultimately deposited. And these are typically referred to as allochthonous materials, in that they represent solid materials that are brought into the basin of deposition from outside basin of deposition. Now again, the kind of a clear-cut picture that you can put in your head about that is the Mississippi River and the Gulf of Mexico again. All of the stuff that's been generated by weathering and erosion on continental North America, all of that stuff that ends up in the Mississippi and is brought down the river and dumped at the mouth is being brought from North America, continental North America, and dumped into the Gulf of Mexico. So in that sense, they are considered to be allochthonous materials. They're brought from outside and put into the basin. As we'll see a little bit later on, when we look at carbonates, which is what I'll talk about today, we will be dealing with autochthonous materials. In other words, sedimentary materials that form within the basin of deposition. They're not brought in from somewhere else. they actually form within the basin. And if you look at terrigenous rocks, 99% of them are made up of silicate-based minerals. Not particularly surprising given the resistance of silicate-based minerals to breakdown by weathering and erosion. The remaining 1% is non-silicate, and the presence of these less stable materials is generally related to some form of rapid erosion, transportation, deposition. In other words, it occurs very quickly so that there's not enough time to break those materials down. And finally, when we classify terrigenous sedimentary rocks, we classify them on the basis of composition or mineralogy and grain size or particle size. And so here we have a picture of a conglomerate where you can clearly see the clastic texture. These are clasps or fragments, okay? And you can see they have different size, shape. This one is particularly well-rounded, for example. This is a much larger particle, and you can see finer grain particles in between. And the whole shooting match is kind of stuck together because it's obviously undergone liquefaction. So when we talk about a clastic texture, that's what we're talking about, where you can see the individual particles that were once separate, individual behaving fragments that have been brought together and ultimately stuck together. Okay, so what I want to spend my time this afternoon is getting into the biogenic, organic sedimentary rocks, biogeochemical rocks, if you like. They form by precipitation of minerals from bodies of water through a variety of chemical or biochemical processes. So it's important to remember that in nature, when you have precipitation occurring, for a long time people thought about the precipitation as a purely inorganic process, but the more we look at these rocks, the more we come to recognize that there is a biogenic imprint of significant proportions, dominantly through bacterial interference, if you will, biological interference that enhances the precipitation process. And there are 5 kind of basic groups of these biochemical sedimentary rocks. And the one, obviously, that we'll spend the rest of this afternoon looking at are the carbonates, but we also have a group of rocks known as evaporites. There are siliceous sedimentary rocks such as the cherts, and there are iron-rich sedimentary rocks, and finally there are things called phosphorites, and if you go into the literature you can find more. But in general terms, this grouping of 4 or 5 different types cover a large range of the biochemically generated sedimentary rocks. As I say, we will look at carbonates, principal reason being that they are volumetrically the most important of the biochemical sedimentary rocks. The carbonates account for about 14 or 15% of all sedimentary rocks. So clearly, terrigenous sedimentary rocks are the major players in the game in terms of their volumetric abundance. And if you look at this pie diagram right here, you see in the tan colors what we would just generally put under the category of terrigenous sedimentary rocks, and in the blue we are dealing with the carbonates, and then those other ones that I showed would add up to whatever percentage it would be. But interestingly, when you look at this from the overall perspective, recognize that the most important of sedimentary rocks are the very fine-grained sedimentary rocks, silts and shales, accounted for almost 75%, and the coarser-grained ones, such as the conglomerate that I just showed you in that earlier slide, sandstone conglomerates, 10, 11, 12% of the sedimentary rock record. So limestones and dolostone, which are magnesium-rich carbonates, represent a relatively small but fortunately or unfortunately important component of the sedimentary record. So if we look at the carbonate sedimentary rocks, obviously they're made up of carbonate minerals, and all carbonate minerals form by combining the divalent cations with the complex carbonate anion, the carbonate anion shown there in that first bullet. And the most common of the divalent cations are calcium and magnesium that combine to give you calcium carbonate, which is going to be either calcite or aramid, is a polymorph of calcium carbonate. And you have magnesium carbonate either in the form of magnesite or dolomite, shown by this formula right there. There are many other carbonate minerals that exist. They are less common, and you're not likely to come across them, but you should be aware, for example, iron carbonates or siderites as they're known, strontium carbonates giving rise to strontianite, manganese carbonates, rhodochrosite. You guys are close enough to mineralogy that you might even remember some of these. Barium giving you witherite, lead, cerussite, and zinc giving you smithsonite. So these are all carbonate minerals, and obviously the major difference is the cation that forms and gives rise to them. So the two kind of important carbonate minerals from our perspective in terms of what we see in the rock record are calcite and aragonite, which are polymorphs of calcium carbonate. And in the upper picture we see a chunk of calcite, and this particular mineral that we see down there is aragonite. Calcite has a rhombohedral lattice, and aragonite has an orthorhombic lattice, so it has different atomic structure, but with the same basic chemistry, obviously. A fairly common occurrence in the carbonate field of the carbonate area is magnesium is a common substitute found in the atomic structure of the different varieties of calcite, and so you have slight variations in that you have what's known as high magnesium calcite, which contains a little bit more than 5% of magnesium, up to as much as 15, 20, 25% magnesium. And that category of calcite is known as high magnesium calcite. And then, as you would suspect, if that's the case, there must be something known as low magnesium calcite, and that is going to be the form of calcite that is less than 5%, or has less than 5% magnesium present in its structure. Dolomite, another carbonate mineral, the formula that's given you there, you can see the calcium and magnesium in the structure. Ideally, in a theoretical sense, should contain a 54% of calcium and magnesium. In reality, in nature, the average dolomite is somewhat unbalanced with respect to the theoretical ideal, with about 56% calcium and about 44% magnesium in structure. And the origin of dolomite is one of the interesting things in sedimentary geology. You have the basic argument as to whether dolomite can be formed as a primary mineral, or is it merely the product of diagenetic changes. And Dr. Chappitz might talk about that on Thursday. Yeah.
So, what exactly would you call it as well as magnesium that was in 20 and 30%? Right? If it was, say, 30% magnesium and 30% phosphorus.
Well, it doesn't get that in a chemical sense. The ability of the magnesium, how it relates to the lattice structure, is what determines that you've got these populations that tend to be separate from each other. The different polymorphs of calcium carbonate have different stabilities, and the least stable of those is the aragonite. The next most stable is high magnesium calcite, and the most stable of all of the carbonate minerals is the low magnesium calcite. And this is important in part because of what is preserved and how it is preserved in the rock record. It particularly influences the preservation of fossils. Many organisms, many invertebrate organisms that have skeletons of calcium carbonate, very often those skeletons are aragonitic in nature, but because of the instability of the aragonite, it tends to break down over time, and the aragonite is diagenetically transformed into a low magnesium calcite form. And that can often, when that happens, that can often destroy the internal structure of the original shell material. So you preserve the overall morphology of the shell, but the internal structure is often lost by virtue of the transformation into low magnesium calcite. So where does calcium carbonate form in a depositional sense? EOD, if you've been in the military recently, that would be explosive ordnance devices, but this is geology, so that is environments of deposition. Okay, so what are the environments in which carbonates form? It's important. So climate is very important. Carbonate deposition is optimal during greenhouse climate. There are two major climatic states on the planet, the greenhouse and the icehouse climates. We are currently living in the icehouse climate in a significant interglacial period of an icehouse climate, admittedly, but we are living in an icehouse climate. Carbonates, however, are most abundant in terms of their origin of formation during greenhouse climates. So if we look at the rock record, we find that there are times stratigraphically where we have a lot more carbonates in the record than other times. So for example, in the Ordovician to Devonian, there were lots of carbonate deposition, and in the Jurassic Cretaceous we see lots of carbonate deposition. And if you look at a kind of a graph of this, it's kind of a busy graph. It shows a number of things. The middle thing listed under climate shows the climate either of the icehouse, greenhouse, and here we are today in the icehouse, age on the horizontal axis going from old to young. So this is the Phanerozoic, the last 542 million years worth of Earth history, and you can see during the Ordovician, Silurian, Devonian, you're in greenhouse, so you have lots of carbonates. You have a little excursion in here where there was a cooling period that resulted in ice caps. Remember, these are just black dots that were Carboniferous, Permian, Triassic. You're in an icehouse climate, and then the Jurassic Cretaceous, you're back in the greenhouse climate. And the first slide that I had on the screen today was of chalk deposits, the white cliffs of Dover, they being Cretaceous age deposits. that form during the greenhouse climate. The lower part of the graph shows large-scale sea level changes throughout the Phanerozoic, and you'll notice that there is a relationship between high stands of sea level, low stands of sea level, high stands, and low stands. These are related in part to plate tectonic activity. And the upper part of this diagram is of interest mainly because it shows some of the extinction events or biotic crises that have occurred in the last 500 million years or so. So here, for instance, crisis number 6 is the Cretaceous tertiary boundary, extinction of the dinosaurs and all that other stuff. So climate then is an important component of determining where and how carbonates form. Yeah.
So, is it relatively is it about right to say that whenever the Earth comes from ice ash to a greenhouse or back and forth, there's a major extinction event?
No. Well, it's clear that climate affects biosphere, organisms. The mass extinctions that we were looking at in that previous slide, like the end Cretaceous, reflects an extinction that occurs over relatively short periods of time, very short periods of time in the case of the Cretaceous tertiary boundary. And the argument that climate, although it changes fairly rapidly, is probably not changing at a clip that would be high enough to necessarily account for that. Clearly, organisms respond to climate, but typically, if you make the changes slow enough, many organisms are able to respond and adapt, migrate, for example. Now, plants can't migrate, certainly trees and things of that kind, they can't migrate easily. And so, in that sense, there might be a relationship. And some of the extinctions that we see in the Phanerozoic are related to variations in the climate. But it's not a clear-cut, necessarily one-to-one relationship.
So it does contribute, it's just not.
That's correct. Yeah. Well, when you're in an icehouse climate, ice caps are forming on the continents, and the water that it takes to generate those ice caps causes sea level to fall. Similarly, when you increase the temperature, you go to a greenhouse climate, you melt the ice caps on the continents, and that will cause sea level to rise. Okay? Well, why did it change that? I have no idea. I mean, we went into the greenhouse climate prior to Jurassic transition. And the point I was making in my big lecture that I teach is that the dinosaurs that were around then didn't drive SUVs, for example, and so there are causes, natural causes, if you will, that affect climate and the change of climate. And the change of climate that we are seeing today is in part due to natural causes related to orbital variations in the planet and all these other things, but also related to greenhouse gases, and of course people are generating huge amounts of greenhouse gases, so there are contributing factors. We know from looking at these kinds of graphs that the Earth's climate is very dynamic and it changes in a cyclical fashion through time, so that should not come as a great surprise. The question in the modern debate is how and to what level are we driving it faster than it might normally have occurred? That's the issue of debate today. Not that people say climate isn't changing, and that's nonsense. Of course it's changing. That's what climate does. It's always changing. The question is, what are the driving mechanisms? And so the question you asked is what happens here? I have no idea, but something obviously happens to cause that change. So climate influences where carbonates are deposited. They can be deposited in marine and freshwater settings. Obviously, well, perhaps not so obviously, but the reality is that the greatest volume of carbonates are shallow marine deposits, and the vast majority of carbonates tend to be autochthonous. There's that term. Remember, we talked about alloptonous sedimentary materials being brought from outside the basin into the basin. If the materials formed within the basin, they are described as being autochthonous in nature. And this is an important point because it reduces the emphasis on hydraulic transport of sedimentary particles. Because if you look at terrigenous sedimentary rocks, one of the things that you look at, for example, is grain size or particle size, because that reflects energy conditions needed to move grains. Larger grains need higher energy to move them than the finer grains. Well, when we look at carbonate rocks and the particles that we see with them, they form in place in the basin. And so if you have a large chunk of a carbonate particle, such as a oyster shell, that does not indicate high energy hydraulic transportation conditions. It merely reflects the fact that that chunk of calcium carbonate grew in place. Yeah.
Two questions. When you say most form in a shallow marine, what do you mean by shallow? Do you mean
10 meters or less.
10 meters or less?
Yeah.
All right.
But they can form in deeper waters than that, but the bulk of them tend to form in those shallow waters. And the deeper it gets, the lower the volume that's generated or is precipitated.
Also, with precipitated carbonates, larger particles or smaller particles don't give any boost on energy level, which is found in place.
It's not that they don't give you energy information. You have to look at them carefully to recognize that they may not be the product of high energy or low energy.
Versus the other type of originals, you see what particles.
Yes, you have to deal with higher energy, yeah. So if we look at the various factors, environmental factors that affect carbonate deposition, they tend to form in warm, shallow, clear marine waters. So when you go on your vacation in the Caribbean, those nice waters are often the sites of carbonate deposition. Agitated water is important. Typically experiencing relatively high rates of evaporation, which would address warmer conditions. I think back to the greenhouse climate argument, and a decrease in carbon dioxide concentration, which typically happens in shallower water. In deeper waters, carbon dioxide, by virtue of pressure differences, can be held in greater concentrations. Shallow waters with agitation and so on and so forth can result in the release of carbon dioxide. And so if you look around the world today where we see carbonates forming, here off the southeast coast of the US, we have the Bahamas, the Bahama platform, the white milky substance that we see on the Bahama banks, oolite shoals. You typically see carbonates formed either on isolated major offshore banks, of which this is one, or of course you can have a shelf that's attached to a continent, and it has a shelf margin that may be characterized by the presence of coral reefs of that kind. So the bulk of carbonates that we see forming today are forming essentially what we can refer to as tropical to subtropical conditions, 30 degrees north and south of the equator. and in shallow marine settings, usually less than 10 meters in depth. Now, as I pointed out earlier, that doesn't mean carbonates can't form below 10 meters. Volumetrically, it's the upper 10 meters where you see a lot of the carbonates form. And if you look at the distribution of hermatypic reefs around the world today, you will see that they sit broadly in this equatorial zone. Red Sea, Great Barrier Reef off eastern Australia, and the reefs, coral reefs of the southeast Pacific are generally well populated with coral reefs. And these reefs reside, when we talk about, remember, clear warm water. Well, the clear water is important because that determines the depth of the photic zone. The photic zone being that zone in the oceans where light penetrates. Why does light come into play here? Well, light comes into play because corals, ironically, corals of course are animals and they're not necessarily particularly interested in light. Plants, on the other hand, are, because they need light for purposes of photosynthesis. And most corals have symbiotic algae in their soft tissues. And so a healthy, thriving coral has to be in the photic zone for the symbiotic algae to photosynthesize and do all the other good stuff. And most of what we call coral reefs today are in fact dominated by calcareous algae more so than the corals themselves. So there are a lot of plant life associated with these reefs. So one of the largest reefs in the world is the Great Barrier Reef off the coast of northeast Australia, stretching for hundreds of kilometers, obviously. Fringing reefs that form at the edge of continental shelves are the distinction between the isolated platforms that we showed in that earlier slide. Fringing reefs, and this is one of the interesting aspects about carbonates, of course, is that because they're autochthonous, because they're forming in the basin of deposition, if you have subsidence of the sea floor, the coral reefs, under most circumstances, can precipitate and keep pace with the subsidence, maintaining a relatively constant sea level with respect to the reef itself. They tend to grow up into the surf zone. There are circumstances where subsidence can be rapid enough that you can actually drown a reef and kill it off. And there are examples of that in the geologic record. So this is a nice example of how these kinds of carbonates as sedimentary deposits are different from the terrigenous materials we talked about, because they grow within the basin and they can adjust to the subsidence history of the basin in a way that terrigenous sediments can't necessarily do. So one of the areas where we see coral reefs developing in the rock record is in association with atolls that form these nice lagoons. And these structures begin life with volcanic activity, where a volcano reaches to or actually builds above sea level, and the volcano may become extinct. In the right finite conditions, carbonates will form in the shallow waters around the volcano, and if the subsidence of the volcano occurs as it drops deeper and deeper, related to thermal cooling of the lithosphere, for example, the reefs that form there keep pace with the subsidence of the extinct volcano. And so in the Pacific, where you see lots of these kinds of the Southwest Pacific particularly, where there's a lot of volcanic activity, the development of atolls and their associated lagoons is quite a common feature. So you can look at Bora Bora as an example. There is I believe it's an extinct volcano that's there, and then we have the lagoon and the reef surrounding it. You can see the clear blue water, the shallow water, and it's deepens off in this direction. Now, you notice I've got a statement here saying the atoll can be divided into 5 basic zones, and I've got 4 listed. That's fine. I'll show you the 5th one in the next slide. So there are different parts of the reef where the carbonates form. And so here you've got the back reef 1, reef flat 2, reef set 3, reef front 4, and 4 left 5. So that's the 5. And you can see there's a depth difference. Obviously, the reef crest typically will be in the surf zone. This would probably be normal wave base, storm wave base obviously would be deeper than that. And the conditions, the environmental conditions associated with the development of this reef will dictate the kinds of corals that form. Where you get below normal wave base, the corals are often relatively fragile, branching types of corals. In the reef crest, where there are pounding waves, the corals tend to be more massive to be able to withstand the pounding of the waves. And you can see in that picture in the top right, when we talk about clear, warm, shallow, agitated water, that's kind of the conditions in which carbonates like to form. So in talking about the distribution of where carbonates form in a geographic sense, we see they tend to exist in this equatorial zone around the planet. The distribution of carbonates vertically is shown in this slide, where we've got water depth typically, and then concentrations of calcite and aragonite as we go from sea level down to this 3, 4, and 5 kilometers water depth. And what happens as you go into deeper and deeper waters, because of the higher pressure conditions and the increased concentration of carbon dioxide, it results in a geochemical environment that is not good for the carbonates. And so as you go deeper and deeper, you see the aragonite gets less and less and less because it starts to dissolve. And this first line there is called the aragonite lysocline. That is the depth where we begin to see significant dissolution of aragonite. And by the time you get down to the aragonite concentration depth, ACD, the aragonite is simply dissolved at that point. It is very rapid dissolution. Calcite, because it's a somewhat more stable form of calcium carbonate, undergoes the same sort of problem, except it can survive to somewhat greater depth. So you see a significant increase in calcium carbonate or calcite dissolution by the calcite lysocline. And then you get to this point, which is the calcium carbonate or the calcite concentration depth, below which calcite typically doesn't occur. And there are circumstances where you can get carbonates beneath that, but typically it's because they're transported in en masse by fluidity currents, things of that kind. In other words, you dump the calcite in there so quickly that the chemical reaction to dissolve it can't occur fast enough to do that. But if you were a foraminifera that lives in surface waters and you secrete a test of calcium carbonate and you die, that test sinks through the water column, it will never make it to the bottom if the bottom is equal to 4 kilometers. Because once it hits this line, it starts to dissolve, and by the time it gets to this level, it's gone completely. So there are factors that influence the geographic distribution of carbonate deposition, and also there are depth factors that come into play also. So when we look at carbonates, the major difference between carbonate and ferruginous rocks is a fairly obvious one. And what is the major difference between carbonates and the ferruginous rocks in terms of classifying them?
One's a porphyry,
No, you can get allochthonous carbonates, ironically. Not many of them for obvious reasons. What's the other? No, you've had one shot. Let's give somebody else a chance.
Okay.
What's the basis of classification of ferruginous rocks? We have pardon? The what? No, we talked about the classification of ferruginous rocks. What are the two things we use? Grain size and composition or mineralogy. Well, when you look at carbonates, calcium carbonate is calcium carbonate is calcium carbonate. That's not strictly true because we have aragonite, high magnesium calcite, low magnesium. There are mineralogical differences, but in general terms, when you're looking at limestones, you're looking at what we can describe as monomineralic rocks. They're made up dominantly of one mineral. So what is an important component of the classification of ferruginous sedimentary rocks, mineralogy and then grain size, is not available to us when we deal with carbonates. Because they're dominantly monomineralic, the texture of the rock becomes a much more important component in classifying carbonate sedimentary rocks. So textural considerations are very important when it comes to identifying and naming carbonates. So when we look at limestones, the calcite that we see present in a limestone is typically present in two distinct textural forms. We have what are known as allochems, which is a fancy word for a carbonate grain or carbonate particle, and we have orthochems, which are essentially dominantly spheric calcite and micrite, where micrite is a term used, the full term is microcrystalline calcite. Micrite is a shortened version of microcrystalline calcite, and by that we mean calcite crystals that are less than 4 microns in size. In other words, obviously very fine-grained calcium carbonate. Okay, so allochems. Allochems are particles of calcium carbonate that form in a variety of ways, and we'll look at the variety of ways in which they form in a minute. And after they are formed in the shallow, warm water and marine settings, they can be moved around by current activity and deposited as clasts. And that's why some biochemical sedimentary rocks have a clastic rather than a non-clastic texture. And there are two major groups of allochems that are recognized or identified. First are the skeletal allochems, and obviously the second category would be non-skeletal. And obviously when we look at skeletal allochems, we are looking at fossils essentially. The skeletons involved can be an entire skeleton, which is particularly true when you deal with microfossils such as forams and other planktonic types, or they can be skeletal fragments, which typically is the case where you have say, a clam or a gastropod that is in its own right a sizable chunk of calcium carbonate, but through a variety of biological or physical activities, that skeleton gets broken into smaller and smaller pieces. So whole skeletons typically are microfossils. They tend to have the entire skeleton preserved, which is very useful because it allows you to identify them quite accurately, whereas a fragment, depending on the size and the shape of the fragment, you might not even be able to tell which larger group it belongs to, let alone be able to identify the species. The skeletal alatens, which I suppose if I think about it, is another term for fossils, or different fossils in different states, are extremely important items because, in addition to helping you in a sedimentological sense in terms of identifying and naming the carbonate rock that you're working with, you can use the information from these skeletons for biostratigraphic purposes, age dating, if you will, of the rock, and also for to extract paleoecologic information from the rock. Because ultimately, one of the interesting things about sedimentary rocks is one of the things that people want to do and like to do is to use these rocks to extract information from them that tell you about the conditions under which the sediment accumulated. We've already talked in terms of terrigenous rocks where grain size and energy can be related, high energy, low energy. Skeletal alatens are important to us because, unlike a sand grain, a silica sand grain, a quartz sand grain can tell you stuff about hydrodynamics, tell you about current activity because the grains could be moved to form cross-bedding, for example. But a quartz grain doesn't give a damn whether it's been washed around in fresh water, salt water, warm water, cold water. It doesn't care. It just responds to what's going on in the environment. Organisms are sensitive to the environment. They're sensitive to temperature. They're sensitive to salinity. And they're also sensitive, obviously, to current activity because they can be moved around just like the sand grain. But because they're sensitive to a wider range of environmental factors, it makes them of more interest to us and of more importance to us, particularly from the paleoecological consideration. In other words, being able to extract information about the environment at deposition. Okay, so as I pointed out, that microfossils are most likely to be preserved whole, where the larger invertebrates are typically present as fragments. And so here's an example. A lot of calcium carbonate is in this picture. This kind of monotonous purplish color, whatever it is micrite, essentially. So that's the orthochem present in this picture. This is a shell of, I'm not quite sure, it's probably a floran. These would be the living chambers of the organism. Obviously, the soft tissue is decayed. Water has gotten in there and precipitated this starry calcite, which is filling the chamber. So this is a biogenic alchem. Obviously, it's a fragment, well, actually it's not a fragment. This is the whole specimen. These guys right here typically represent fragments of shell material that have been broken up by mechanical means, for example, and obviously nondescript in terms of your ability to identify. This guy, obviously, if you know the taxonomy, you can extract information about those guys, yeah.
Isn't that helpful species?
Pardon?
Isn't that helpful species?
Oh, you're talking. I don't know that the preservation there is good enough to identify that below a certain level. I'm not a forearm expert, so I don't know. Yeah. Oh, this actual rock. Yes, this would be a biomicroid. And we're getting ahead of ourselves. We'll talk about the classification schemes in a little bit, but yes, this would be an example of a biomicroid because you have biological alkenes embedded in a fine-grained micritic matrix. This is another process, again, of nondescript sense because it's undergone a process known as mimetization, in which the internal structure of the skeleton has been destroyed by algal activity. But again, you see the body cavity is filled with sparry calcite. The blue coloration here is a dye, is an epoxy actually, where if you're dealing either with loose sediment or poorly cemented rocks, they often embed them in an epoxy to make them hard, where you can cut them and polish them to make thin sections of them. So you can see on the outside of this alkane, this biological, you can see the cement that has been precipitated on the outside of this organism. And you can see the cement contacting this particle with this particle. This would represent in the rock before it was prepared for thin section would be porosity. So the kind of thing oil company people like to see. They like to see lots of holes in the rock because the holes are more important to them than the rock itself, because the holes are where the gas and oil reside, obviously. So if we look at non-skeletal alkenes, there are three major categories that we can look at: coated grains, peloids, and intraclasts. We look at coated grains first. These are particles characterized by the presence of concentric layers of calcium carbonate that form around a nucleus, a central nucleus. And so these concentric layers form the outer parts of what are often spherical or subspherical particles in terms of their overall geometry. They form in shallow agitated water, those conditions that we talked about earlier, and they roll around. And as they roll around in water that is saturated with respect to calcium carbonate, coatings of calcium carbonate form on the particle as it rolls around, building it up into slightly larger sizes. There are three major types, and the types are related to size in a large extent: ooids, piezoids, and oncoids. If we look at the ooids, these are spherical particles. They tend to have a very small nucleus surrounded by these concentric layers of calcium carbonate. They have a size of less than about 2 millimeters. They typically fall into the 0.2 to 0.5 millimeter size range, which is the size of fine sand in the poisonous Wentworth steel type of situation. And as I say, these form on the seafloor by being washed back and forth. Typically form in depths of less than 5 meters. That's in large part because of the agitation component of the environmental setting. And this is what they look like. If you ever there's a beach in Abu Dhabi that I walked on, and the sand on the beach were weird, and it was weird because when you walk on the sand groans as these things rub against each other. They make a very distinctive noise. So you can see some of them are very, very nicely spherical. Others are not as, and this would suggest to me that the nucleus of this fragment was perhaps a shell particle that had a slightly different geometry or shape to it, and that translates into the somewhat irregular, non-rounded or non-spherical shape that we see there. If you look at a thin section, this is an example where somebody's taken individual ooids, sediment if you will, and embedded them in the epox we use of glucose up there, so we can make thin sections of them. But you see that when we talk about the concentric particles, obviously this is what we're looking at in terms of concentric geometry. Piezoids, the second of the coated grain category, they're very similar to ooids in that they have this kind of concentric layering, but they tend to be much larger than about 2 millimeters. They tend to be not as perfectly spherical. The concentric layers tend to be crenulated, irregular, and it's suggested that the crenulation might be related to the fact that there might be some algal interaction associated with the generation of these concentric layers. Wrinkly. Okay. And then finally, oncoids, which are the larger specimens. These are larger than 1 to 2 centimeters, and you can see examples up to the size of your fist and larger. Again, they tend to have a somewhat more irregular shape, and they are also crenulated layers. And these guys are identified as stromatolitic in origin, in which there is a clear relationship between algal activity and the generation of the larger body, the oncoid itself. And so what happens is you have this ball of material sitting on the seafloor, and it has algae living on it. And it kind of gets rolled around. Of course, the larger it is, the more energy you need to roll it around. And as that happens, the algal filaments, which have mucus, sticky substance, tend to attract particles and stick the particles together, and they give rise to these layered structures that are roughly spheroidal in shape. Stromatolites as a whole, there are mat-like structures where algae grow on the surface of the intertidal zone and trap sediment, and you have alternating layers of sediment and algae, giving rise to layered structures. When they're somewhat spherical and can roll around, that's when they fall into the category of being referred to as oncoids. Yeah.
What sort of environments do crystals and oncoids come from? Do they also form in
Yeah, they're typically shallow water phenomena because the concentric nature of them indicates that they're rolling around, accumulating these layers. Okay, so yeah. Yes, shallow, warm, clear, agitated water, fairly shallow depth.
High energy?
High energy, yeah.
All of them? Okay.
Yeah. Okay, I'll stop there, and Dr. Chaffetz will continue from there on Thursday.